To operate from aircraft carriers, an aviation platform requires more than just aerodynamic lift. It requires a structural foundation capable of surviving the most brutal kinetic impacts. The core skeleton begins with massive aluminum alloy bulkheads. This design generates a characteristic barrel-shaped fuselage, prioritizing absolute structural rigidity over minimal frontal area. Piercing through these bulkheads are dozens of longitudinal stringers. They interlock the entire skeleton into an unbreakable, cross-hatched alloy matrix. This is the semi-monocoque architecture, a design that mathematically distributes severe bending and torsional forces evenly across the entire geometry of the airframe. Wrapped around this skeleton is the aluminum alloy skin. In a semi-monocoque design, the skin itself acts as a critical, load-bearing structural membrane. However, at flight speeds exceeding 600 kilometers per hour, even the smallest protruding rivet head creates aerodynamic turbulence, generating massive drag. The mathematical equation is clear. Protrusion equals parasitic drag. Tens of thousands of standard rivets would mathematically steal the aircraft's top speed. Grumman's solution was flush riveting. The manufacturing process demanded that a precise conical depression be countersunk into every single rivet hole. An angled flat-headed rivet is then inserted. The geometric result is a rivet head that sits absolutely flush and uniform with the exterior aluminum surface. When the airflow vector makes contact, laminar flow is perfectly preserved. Zero aerodynamic turbulence is generated across the joint. The manufacturing team, famously known as the Ironworks, applied this meticulous technique to tens of thousands of rivet holes across the entire massive airframe. The structural equation is finalized. Flush riveting combined with a semi-monocoque frame provides absolute rigidity, alongside the lowest possible aerodynamic drag. The core fuselage is complete. But to operate on a carrier deck, an aircraft requiring massive lifting surfaces must somehow solve an extreme spatial dilemma. An aircraft carrier deck is an incredibly scarce geometric plane. The fighter is mathematically required to retract its wingspan at all costs. To solve this spatial dilemma, Grumman engineered a unique folding mechanism that defied traditional geometric constraints. From the wing roots, the algorithm generates the main lifting surfaces. The wingspan of this machine was designed to massive proportions to maximize aerodynamic lift. However, when measured against the coordinates of a standard carrier elevator, a spatial conflict immediately occurs. The wingspan far exceeds the allowable geometric limits. To resolve this paradox, a mechanical masterpiece was engineered precisely at the wing root. X-ray vision exposes the Sto-Wing hinge. The pivot axis is not vertical or horizontal. It is positioned at a highly specific, mathematically complex diagonal compound angle. When activated, a high-pressure hydraulic cylinder floods with fluid, generating a massive kinetic vector that forces the heavy wing structure to break its locked position. Governed by the angled axis, the wing does not simply fold upwards. It executes two simultaneous movements, sweeping backward toward the tail, while physically twisting 90 degrees. This twisting motion directs the leading edge straight down to the deck, allowing the entire flat surface of the wing to rest perfectly parallel and flush against the fuselage. Thanks to the Sto-Wing mechanism, the deck footprint is slashed by a staggering 65%. This allowed vastly more aircraft to be packed into the confined space of a carrier. Yet any mechanical joint introduces a fatal physical weak point. A folding wing risks being literally torn from the fuselage under the massive aerodynamic forces of flight. To overcome this, massive forged steel locking pins are utilized. Driven through thick steel lugs, they mechanically fuse the folding joint back into a solid, monolithic block. During load testing, even as massive lift vectors violently strike the wing surface, the steel pins remain unyielding. Absolute structural integrity is maintained. The spatial dilemma is solved. The diagonal folding system provides minimum parking footprint without sacrificing a fraction of combat survivability. Tested against the elevator coordinates once more, the massive aircraft now fits perfectly within the rigid geometric boundaries of the carrier. The entire wing and load-bearing fuselage geometry is now locked. This immense structure awaits a mechanical heart powerful enough to hurl it into the sky. A massive cylindrical void is mapped at the nose of the aircraft. This coordinate space will house one of the most devastating radial power plants in aviation history. To provide thrust for an oversized airframe, the machine required a colossal power source. The algorithm initializes the Pratt & Whitney R2800 double WASP. This massive engine block is mounted directly to the forward firewall, completely filling the established geometric coordinates. Its geometric architecture is a two-row radial. 18 cylinders are arranged in two staggered circular banks, with 9 cylinders per row revolving around a central axis. X-ray vision strips away the casing. Within each row, 8 articulating rods are mechanically pinned to a single massive master rod. All connect to a shared crank throw. As the engine operates, 18 pistons move in rhythm. The staggered firing order creates perfect kinematic balance, neutralizing destructive vibrations. The linear compression from 18 combustion chambers converges at the center, completely converting into massive rotational torque vectors on the crankshaft. At high RPM, this rotating mass of metal generates immense centrifugal force. Left unchecked, this force would mathematically tear the engine block apart from the inside out. To counter this, geometric counterweights forged directly into the crankshaft swing opposite the pistons, perfectly canceling out the centrifugal forces and stabilizing the machine. Mechanical stability is achieved, but it brings a thermodynamic dilemma. These 18 cylinders constantly generate enough radiant heat to melt the engine itself. The solution lies in microgeometry. The surfaces of the cylinders are cast with incredibly dense forged aluminum cooling fins, multiplying the contact area mathematically. As the aircraft surges forward, the characteristic open-nose design catches a colossal volume of ram air, forcing it directly into the face of the radial engine. Fluid dynamics strip all radiant heat from the metal surfaces. This purely air-cooled system completely eliminates the fragility of liquid coolant radiators. This superheated airflow is then violently expelled through adjustable cowl flaps, allowing the pilot to precisely regulate the engine block temperature. With a stable thermodynamic baseline, the double WASP engine officially reaches its design output: 2,000 horsepower of pure kinetic thrust. 2,000 horsepower is sufficient for low altitudes, but to maintain dominance in thin air, this machine incorporates a highly sophisticated air compression system mounted behind the block. 2,000 horsepower is the baseline at sea level, but as the aircraft climbs to tactical altitudes, a severe environmental constraint emerges: atmospheric pressure. At 20,000 feet, air density drops drastically. The fluid dynamic vectors become sparse, mathematically depriving the engine of the oxygen required for maximum combustion. Without intervention, the engine suffers severe oxygen starvation. The mathematical output plummets, stripping the heavy fighter of its primary advantage. To reclaim this lost energy, a massive forced induction system is bolted to the rear of the crankcase. The two-stage, two-speed mechanical supercharger. X-ray reveals the internal impeller. Driven by a complex gear train connected to the crankshaft, this geometric turbine spins at incredibly high RPMs. The sparse high-altitude air is sucked into the blades and violently compressed, mathematically restoring sea-level density to the oxygen vectors before they enter the cylinders. But compressing a gas inherently generates heat. The dense air charge becomes superheated, creating a new thermodynamic bottleneck within the intake manifold. Despite the thermal penalty, the mathematical volume of oxygen succeeds. The supercharger restores the full 2,000 horsepower, even at 20,000 feet. But survival in combat sometimes demands breaking the limits. When the pilot pushes the throttle past the red line, war emergency power is activated. Forcing more fuel and superheated air into the cylinder creates a lethal physics problem. The extreme temperature causes the mixture to detonate prematurely, threatening to shatter the piston. To bypass this thermal limit, Grumman integrated a chemical intervention. A specialized tank is mounted behind the firewall, holding a precise mixture of water and methanol. During WEP, this fluid is injected directly into the intake manifold, mixing with the superheated, highly compressed air charge. As the water evaporates, it absorbs massive amounts of thermal energy through the latent heat of vaporization. The hot air charge is instantly quenched, becoming cool and incredibly dense. With the detonation threshold mathematically bypassed, extreme amounts of fuel can be burned safely. The engine's output violently spikes past 2,200 horsepower. To convert 2,000 horsepower into kinetic forward motion, the aircraft relies on a massive propulsive mechanism. The Hamilton Standard Propeller Hub locks onto the main shaft. From this hub, 3 immense aluminum blades extend outward. The total diameter spans over 13 feet, an absolute geometric necessity to absorb the engine's extreme output. As the engine engages, immense rotational torque vectors are transferred directly into the hub, spinning the colossal blades up to operational RPM. A microscopic cross-section reveals the physics. Each blade is essentially a rotating wing, featuring a precise aerodynamic airfoil geometry designed to slice through the atmosphere. Through aerodynamic lift principles, the rotational torque is mathematically converted. The pressure differential generates massive forward-facing thrust vectors, pulling the entire machine forward. However, as the aircraft accelerates to high speeds, a critical aerodynamic dilemma occurs. The relative velocity of the incoming air drastically alters the physics of the blade. At high forward speeds, a fixed blade effectively loses its bite on the air. Aerodynamic resistance drops, and the generated thrust shrinks dramatically. With less air resistance holding it back, the massive engine begins to spin out of control. RPM spikes violently, mathematically threatening to destroy the internal cylinders. To prevent catastrophic failure, Grumman utilized a Hamilton Standard constant speed governor, a brilliant mechanical computer hidden directly behind the propeller hub. Inside the governor, centrifugal flyweights spin with the engine. As RPM increases, centrifugal force mathematically throws these weights outward, mechanically sensing the overspeed condition. This outward movement opens a precise pilot valve. Highly pressurized engine oil is immediately routed through the hollow propeller shaft and straight into the hub dome. This hydraulic pressure physically rotates all three massive aluminum blades along their longitudinal axes. The blades increase their pitch, taking a much deeper geometric bite into the incoming air. The increased aerodynamic resistance instantly loads the engine. Massive thrust vectors are restored, and the engine RPM is mathematically forced back down into the optimal green zone. This entirely automated feedback loop forms the ultimate propulsive equation. Constant RPM plus variable pitch equals mathematically optimal thrust at any airspeed. With pure thrust successfully generated, the kinetic energy must now be weaponized against gravity. The blueprint shifts focus to the colossal geometric lifting surfaces of the main wings. With thrust established, the kinetic energy must be converted into flight. The algorithm highlights the immense geometric lifting surfaces of the main wings. However, this airframe faces a severe physical constraint. Fully loaded, it possesses a massive gross weight of nearly 6 tons. Gravity violently pulls the geometric structure downward. To overcome this gravitational penalty, Grumman engineered a colossal lifting surface. The calculated wing area spans an enormous 334 square feet. But surface area alone is not enough. The secret to its aerodynamic capability lies within the precise geometric profile of the wing. A cross-section reveals the NACA 23015 airfoil. This specific mathematical contour features a thick, blunt leading edge designed for maximum lift at lower speeds. As the aircraft is pushed forward by the propeller, fluid dynamic vectors strike the leading edge, mechanically splitting the airflow over the top and bottom surfaces. Due to the pronounced upper camber, the air over the top accelerates, creating a zone of low aerodynamic pressure. Meanwhile, high pressure builds underneath. This pressure differential mathematically attempts to equalize. The high pressure pushes upward toward the low pressure, generating massive vertical lift vectors. Multiplied across 334 square feet, the total kinetic lift vastly overpowers the 6-ton gravitational penalty, lifting the immense airframe into the sky. However, landing on a carrier deck requires flying at incredibly low speeds, with a high angle of attack. On standard wings, this steep angle causes the airflow to detach, resulting in a fatal stall. This is where the NACA 23015 excels. Its blunt, thick leading edge mathematically forces the airflow to remain attached to the upper surface, refusing to stall, even at extreme angles. Because lift is maintained, the stall velocity is kept exceptionally low. This grants the pilot docile, predictable handling during the most dangerous phase of flight, the carrier approach. The aerodynamic equation is solved. Massive surface area combined with the NACA 23015 profile yields supreme lift capacity, neutralizing the weight penalty. The machine has achieved absolute kinematic equilibrium. Thrust defeats drag, lift defeats gravity. It is now a fully functional aviation platform. With flight mechanics established, the blueprint must secure the single most critical component on board, the central human processing node. With flight mechanics established, the blueprint must secure the single most critical component on board. The algorithm isolates the central volumetric space of the fuselage. Into this space, the central processing node is inserted. This singular unit is responsible for all tactical, navigational, and thermodynamic calculations during flight. However, this node is incredibly fragile. A kinetic threat simulation reveals extreme vulnerability to high-velocity ballistic vectors approaching from the rear hemisphere. To neutralize this, Grumman integrated absolute structural brute force. A massive geometric plate of cast steel armor is bolted directly behind the node. When the kinetic vectors strike, the sheer density of the steel geometry denies penetration. The ballistic energy is mathematically shattered, leaving the central node completely untouched. However, ballistic threats are omnidirectional. A frontal assault simulation directs kinetic energy straight through the forward optical canopy. Standard aviation plexiglass is replaced here with a geometric anomaly, an exceptionally thick, flat block of 38mm bullet-resistant glass. When the forward vectors strike, the outer geometric layers shatter to dissipate the energy, but the sheer density of the block mathematically absorbs the impact, halting the projectile entirely. To complete the perimeter, additional steel geometric plates are layered underneath the node, creating an armored lower tub to deflect anti-aircraft fire from below. This complete encapsulation transforms the cockpit from a standard seating area into an absolute geometric vault, securing the node's survivability. Despite this massive shielding, optical capability is perfectly preserved. Because the 38mm glass is a mathematically flat plane, line-of-sight ray tracing passes through with zero optical distortion. But this brute force philosophy extracts a heavy cost. The sheer mass of the steel and glass generates massive downward gravitational vectors, heavily penalizing the aircraft's weight limit. Yet, the equation remains balanced. The colossal aerodynamic lift generated by the immense wing area completely offsets this armor penalty, allowing the machine to carry the vault with ease. The mathematical synthesis is finalized. Extreme armor mass, fully supported by supreme aerodynamic lift, equals absolute node survivability. With the central processing node secured, the algorithm must now address a highly volatile chemical vulnerability housed deep within the lifting surfaces. To sustain the massive 2,000 horsepower output, the aircraft requires a vast chemical energy reserve. The algorithm maps the internal voids of the fuselage and wing roots. Into these coordinates, thick, heavy geometric bladders are inserted. These main fuel cells house the highly volatile aviation fuel required for long-range combat operations. X-ray analysis reveals the interior, rapidly filling with highly active fluid dynamic vectors, representing hundreds of gallons of high-octane aviation fuel. However, housing this much volatile liquid creates a massive vulnerability. A kinetic threat simulation introduces a high-velocity ballistic vector striking the tank wall. In a standard metal tank, a puncture guarantees a catastrophic leak. The volatile fluid vectors vaporize into the fuselage, immediately resulting in mathematical and structural annihilation. To prevent this, Grumman utilized advanced chemical engineering. The tank wall is constructed from 3 distinct geometric layers, completely eliminating traditional metal shells. The critical component is the thick middle layer. It is composed of raw, untreated natural rubber, or latex, a highly reactive material purposely placed within the barrier. When the kinetic threat strikes, the bullet still pierces mathematically through all 3 layers of the bladder, opening a puncture channel. Aviation fuel begins to leak into the channel. However, the moment the volatile fuel makes physical contact with the exposed raw latex, an immediate chemical reaction is triggered. The untreated rubber absorbs the fuel and rapidly swells. The geometry expands volumetrically inward, physically swelling to block the puncture channel. Within seconds, the breach is completely sealed. The highly volatile fluid is mathematically contained, halting the leak entirely. Even under sustained ballistic assault, the chemical reaction patches every hole instantly. The threat of a catastrophic in-flight fire is mathematically reduced to near zero. But these multi-layered rubber bladders are incredibly heavy. Once again, Grumman accepted a massive structural weight penalty to guarantee absolute survivability. And once again, the colossal lift of the wings nullifies the weight penalty. The equation is clear. Chemical expansion ensures absolute fluid survivability. With the central node and vital fluids physically secured, the blueprint now shifts from absolute defense to absolute offense. The algorithm targets the outer wings. With the defensive parameters mathematically established, the algorithm now shifts to absolute offense. Precise coordinates are mapped across the outer wing panels. Into these voids, the blueprint integrates a devastating arsenal. 6 M2 Browning 50 caliber machine guns are locked into the airframe, 3 mounted within each wing. A top-down analysis reveals a staggered geometric layout. The weapons are offset diagonally to fit mathematically within the aerodynamic tapering of the airfoil. The ammunition is the 12.7mm cartridge, a massive, heavy kinetic penetrator carrying immense destructive potential. To sustain fire, immense internal space is required. Enormous volumetric bays are mapped directly behind the weapons, designed to store 400 rounds per gun. Heavy, continuous geometric belts link the storage bays to the receivers. However, feeding this massive weight of brass and lead into the weapon requires significant physical force. X-ray analysis reveals the internal mechanism of the Browning. It utilizes a short recoil operation. The geometric bolt and barrel extension are locked together. Upon ignition, thermodynamic expansion violently expels the projectile forward. But according to physics, every action dictates an equal and opposite kinetic reaction. A massive recoil vector strikes backward. This immense kinetic energy is harnessed, physically driving the heavy bolt and barrel assembly backward to unlock the action. As the bolt travels rearward, an extractor physically rips the spent brass casing from the chamber and forcefully ejects it from the mechanism. Simultaneously, this same recoil energy drives a feed pawl. It mechanically grabs the heavy ammunition belt and physically drags the next massive cartridge into position. A return spring slams the bolt forward, chambering the new round. The cycle instantly repeats, generating an automated, blindingly fast mechanical loop. Multiplied across 6 independent weapons, this recoil-operated automation unleashes a devastating continuous stream of 12.7mm ballistic vectors into the airspace ahead. The weapon's mathematical logic is finalized. The gun utilizes its own violent kinetic recoil to physically drag the immense weight of its ammunition, automating its own destruction loop. The internal mechanics of the arsenal are secured. However, having 6 weapons spread across an enormous wingspan introduces a critical geometric problem. How do these parallel vectors hit a single target? If the 6 wing-mounted weapons are aligned perfectly parallel to the fuselage, a severe geometric flaw emerges within the ballistic physics. Because the weapons are spread across an immense wingspan, a small, distant geometric target can literally slip mathematically through the wide gaps between the parallel bullet streams. The equation is absolute. Parallel vectors resulting from a wide, wing-mounted arsenal equal total tactical failure. To solve this, the internal mounting hardware is adjusted. The geometric wireframes of the machine guns are physically angled slightly inward, towing toward the aircraft's central axis. Because each weapon sits at a different distance from the center line, each mount is mathematically calibrated to a highly specific fractional inward angle. These angles are not arbitrary. They are calculated to target a highly specific spatial coordinate far ahead of the aircraft. A dimension line measures the distance. The coordinates are locked to a standard focal point exactly 300 meters ahead of the machine. The 6 weapons open fire. Now, governed by their angled mounts, the ballistic streams project inward, traveling along precise converging mathematical trajectories. At exactly 300 meters, all 6 streams arrive simultaneously. They physically intersect, creating a geometric point of absolute convergence. By overlapping the streams, the aircraft concentrates the kinetic energy of 6 heavy machine guns into a single, blindingly dense focal point. This is the ultimate kill zone. When an enemy geometric node enters this specific coordinate space, it is struck by the combined mass of all 6 weapons simultaneously. The structural integrity of the target is mathematically and instantly annihilated. However, this geometry dictates a strict engagement window. Beyond the 300-meter mark, the vectors cross and spread wide, drastically diluting the kinetic density. The offensive algorithm is secured. Angled wing mounts combined with a fixed geometric distance create an inescapable zone of lethal ballistic convergence. With total air superiority established, the machine must eventually return to the deck. The algorithm now targets the extreme mechanical complexity of the landing undercarriage. To return safely to the deck, the machine requires a robust undercarriage. The algorithm isolates the geometric coordinates beneath the wing roots. A massive, heavy-duty geometric strut and tire assembly is inserted. However, stowing this massive appendage presents a severe spatial paradox. If the gear folds straight up, it immediately collides with the internal ammunition bays. The geometric volume of the wing is already entirely consumed by the offensive arsenal. To bypass this, Grumman engineers designed a brilliant kinematic mechanism. X-ray vision reveals a specialized rack and pinion gear assembly integrated directly into the pivot trunnion. When the hydraulic actuator is engaged, immense fluid pressure generates a pulling vector, physically drawing the massive steel strut backward into the fuselage recess. As the strut swings backward, the pinion gear rolls along a fixed rack. This mathematically converts the linear backward motion into a powerful rotational twisting force. Driven by the trunnion gears, the entire shock strut and the massive rubber tire physically twist along their vertical axis, while simultaneously sweeping backward. A digital protractor validates the kinematics. By the time the strut reaches the fuselage, the tire has rotated exactly 90 degrees. This 90-degree twist allows the massive wheel to lay perfectly flat, nesting seamlessly into a remarkably shallow cavity beneath the wing root, entirely bypassing the internal arsenal. Once nested, precise aerodynamic fairing doors slide shut, completely encapsulating the heavy undercarriage within the aerodynamic envelope. This flush sealing mathematically restores laminar flow to the underside of the fuselage, ensuring zero parasitic drag is generated during high-speed combat. The mechanism is completely reversible. When deployed for a harsh carrier deck landing, the heavy forged steel construction absorbs the massive kinetic impact of a 6-ton machine without buckling. The paradox is mathematically resolved. Complex kinematics provide absolute spatial efficiency, leaving the wing volume entirely dedicated to lethal payload. With the landing gear secured, the blueprint focuses on the ultimate kinetic challenge. Operating from an aircraft carrier demands mechanisms that can survive extreme acceleration and deceleration. The algorithm isolates the extreme rear of the fuselage. It is here that the airframe must absorb the most violent kinetic shocks in naval aviation. Operating a 6-ton fighter from a carrier deck introduces an extreme physics problem, generating sufficient takeoff velocity within a severely constrained geometric runway. The aircraft cannot achieve this solely under its own power. The algorithm highlights highly reinforced structural hooks forged directly into the lower bulkheads. A heavy geometric steel cable, known as the catapult bridle, is attached from the deck machinery directly to these specialized coordinates on the airframe. The engine is pushed to absolute maximum output, generating massive forward thrust. Simultaneously, a holdback fitting at the rear keeps the aircraft completely stationary. The potential energy is immense. This creates extreme tensile stress across the entire fuselage. The semi-monocoque skeleton from Phase 1 mathematically distributes this tearing force to prevent structural failure before launch. The holdback fitting snaps, the deck machinery fires, a colossal kinetic vector surges through the catapult cable, violently accelerating the 6-ton machine forward. The acceleration is mathematically brutal. The velocity spikes from 0 to over 100 knots in a fraction of the geometric distance required for a standard takeoff. Internally, the immense acceleration generates extreme g-force vectors. The central processing node is violently pressed backward into the cast steel armor plate. Upon reaching the edge of the flight deck coordinates, the catapult bridle mathematically detaches. Freed from the external vector, the aircraft pitches upward into the airstream. At this exact coordinate, kinematic responsibility is handed over completely to the aerodynamic profile. The massive wing area instantly generates the required lift vectors to sustain flight. The physics of the launch are validated. Extreme tensile force applied to absolute structural integrity equals a successful carrier launch. Getting into the air is only half the problem. Returning a 6-ton combat machine to a pitching deck requires an entirely different set of violent, decelerative mechanics. To survive the return to the carrier deck, the kinetic energy of a 6-ton machine must be instantly neutralized. The algorithm targets the arresting hook assembly. The aircraft assumes the steep approach angle dictated by its airfoil geometry. It arrives at the deck with maximum aerodynamic stability, but massive kinetic momentum. The arresting hook is deployed. A heavily dampened geometric steel arm extends downward, locking into a highly precise mathematical angle relative to the deck. On the carrier deck, 4 thick, high-tensile steel cables are mapped across the grid. The incoming aircraft must mathematically intersect at least one of these lines. Upon touchdown, the hook scrapes the deck. A successful kinetic intersection occurs. The forged steel geometry catches the third arresting cable. Instantly, a colossal decelerative vector is generated. The entire forward momentum of a 6-ton combat aircraft is violently opposed by a massive backward kinetic force. The velocity mathematically collapses. The aircraft goes from 90 knots to absolute zero in the span of just a few dozen meters. X-ray analysis reveals the structural toll. The extreme tensile load attempts to rip the tail off the aircraft. The heavy semi-monocoque bulkheads distribute and absorb this devastating kinetic shock. The massive kinetic energy is not destroyed. It is transferred. The geometric wire stretches, pulling against hydraulic engines below the deck that mathematically dissipate the aircraft's momentum. Simultaneously, the vertical kinetic shock of hitting the deck is absorbed by the massive hydraulic struts of the undercarriage, preventing the heavy engine block from shattering the frame. Internally, the violent deceleration creates immense forward G-forces. The central node is thrown forward, caught only by the geometric tension of a multi-point structural harness. With velocity at zero, the kinetic exchange is complete. The tension breaks, the cable drops away, and the 6-ton machine is perfectly secured on the deck coordinates. The physics of the recovery are validated. Extreme decelerative force absorbed by absolute structural integrity equals a successful carrier landing. With both launch and recovery mechanics secured, the blueprint must face one final, ultimate test. How does this massive structure handle catastrophic geometric failure in combat? The algorithm prepares for the final phase, subjecting the semi-monocoque Ironworks framework to devastating kinetic ballistic trauma. The ultimate test of the Ironworks philosophy is structural resilience. A simulation introduces a massive, dense swarm of incoming kinetic vectors. The vectors strike the right wing. The kinetic trauma is overwhelming. A significant percentage of the aerodynamic lifting surface is violently and geometrically annihilated. With the surface area deleted, the upward lift vectors on the right side drastically shrink. The aircraft experiences severe asymmetrical lift, inducing a mathematical roll towards the damaged side. This imbalance forces immense torsional stress onto the remaining wing root. However, the over-engineered forged steel locking pins of the folding mechanism absorb the trauma, refusing to snap. The assault continues into the tail section. Kinetic vectors obliterate the right horizontal stabilizer, deleting critical pitch and yaw control surfaces. Error codes cascade across the simulation. Lift is compromised. Pitch is unstable. Yaw is drifting. A standard aviation structure would mathematically disintegrate at this point. Inside the armored vault, the processing node intervenes. Extreme physical force vectors are applied to the flight controls, mechanically forcing the remaining control surfaces to their absolute limits. The remaining control surfaces deflect to their geometric maximums. Because Grumman designed these surfaces intentionally oversized, they generate enough compensatory lift to counteract the missing wing area. Furthermore, the sheer excess capacity of the NACA 23015 airfoil proves its worth. Even with 30% of the wing deleted, the remaining geometry generates enough lift to sustain flight. The violent instability is mathematically arrested. The heavily damaged wireframe levels out. Aerodynamic integrity is marginal, but stable. This survival is not a mathematical anomaly. It is the direct result of the Ironworks philosophy. Over-engineered bulkheads, forged steel joints, and immense redundant lifting surfaces. The final aerodynamic equation is written. Structural redundancy combined with excess lift equals absolute combat survivability. The extreme limits of the airframe have been tested and proven. The algorithm clears the battle damage, restoring the geometric wireframe to pristine condition. Now, we will merge all internal aerodynamic and kinetic systems into a single cohesive mechanical synthesis. To truly understand the absolute structural brute force of this aviation platform, the algorithm initiates the final total geometric deconstruction.